the last time that we were all here, we talked about underground mining, which is probably the smallest footprint, but the most dangerous and most expensive. We talked about open pit mining, which has grown in scale as technology gets smarter. We've been able to make much, much, much bigger holes in the ground. Big problems here being the water pollution of all that sediment, and of course that giant funnel that traps water whenever it rains. So groundwater and surface water problems. Did we talk already about strip mining as well? I have to remind you, double check your notes, that strip mining is specific to coal mining. So one particular impact of this is that strip mining, because of the coal, tends to generate hydrocarbon pollution. Hydrocarbon pollution. You know, the coal is associated with petroleum and natural gas, so whenever you're digging around the coal, there's always going to be some oily stuff around, and that's really foul. Did we do this one already? The mountaintop removal? Yes. That's nice. You're so far ahead. I love it. Remember that this is very likely the largest landscape transformation ever done by humans. This is the biggest net habitat impact. If you were looking for the worst activity that humans do, this might actually be it. In terms of the number of people and the number of dollars per unit of habitat area, this is debatably the biggest thing we do to the earth. Sediment pollution is a very big problem. Particulates in the air are a very big problem. To contain all that sediment, you need tremendous impoundment, which itself is a problem because those dams can fail. Did we talk about all this already? Anybody want to double check anything in your notes about any of these before we get to the next step? Okay. I'd like to pass out rocks that you should not lick. You'll notice that all the rocks have these little blue or green stains. Diego Perez is better at my job than I am, so he could identify them, but I forget already what he told me to say. For now, don't pass them back. I want to tell a story about these rocks. Then everybody will see them. That tuna was killer. Yeah. I sliced it into steaks, made like a miso glaze with passion fruit jam. It was really good. Seared. My kids loved it. I loved it. Yeah. And I saw you getting ready. Good move. It doesn't taste like anything. So let's talk about the history of how this got here, and then we'll explain why that's important. So somewhere a gazillion million years ago, there was a mountain range that was weathering, and sediment was eroding, transporting down to a sedimentary deposit, some sort of depositional basin. You could imagine a deep sea trench, a coastal bay, a swamp maybe, where all that sediment and silt was just aggregating like what you see at our beach. I don't know anything about those mountains. A geologist could tell you by looking at this a bunch of characteristics of those historic mountains. I'm not good enough. But I do know that there was sand, and in that sand, every 1 in a billion grains was a little tiny piece of copper. That sedimentary deposit was mixed sand, formed into sandstone. That sandstone was buried under other layers of rock and probably driven under another tectonic plate so that heat and pressure metamorphosed the sandstone into something else. Metamorphosis is heat and pressure, which forces chemistry, so the rock literally changed. It became a totally new rock. That's called metamorphic rock. It started as one thing. Heat and pressure makes chemistry, makes new rocks. Some ingredients left that rock because of the heat and pressure. They off-gassed. They layered out by density. And all those little grains of copper got hot enough to become a liquid. In that metamorphic rock, all the little droplets of copper were squeezed together until they found a pocket that the copper could not escape. And as that tectonic plate rose, it cooled, and that runny liquid copper dried into a seam of copper in quartz. Additional uplift, future weathering and erosion, until in the last 100 years, some human walked up to the quartz and said, hey look, this region of quartz has this neat blue-green copper band that's valuable. We can make pennies or pipes or wires out of that copper. So those humans walked up to that quartz and they hit it with hammers or machinery or whatever and broke up the quartz into these. And the really valuable stuff, they already mined it. But the stuff that has a little bit of copper and not enough to be worth extracting, they sell it to people like me who want to use it for a lecture. What you're all looking at is metamorphic rock, mostly copper. There are other rock types, and if anybody's a rock expert, I apologize. I don't think the details are relevant to what the students need to learn, but I could have blown it in that explanation. I do not have good geology. But you're all looking at what I think is quartz with a little stain of copper. The copper is the bluish green stuff. You shouldn't eat that. It's slightly toxic. Feel free to pass it back. I want everybody to see. Look at how much rock and look at how much copper. Look at how much rock and look at how much copper. If you were to take all the copper out of this rock, what is that? A few milligrams? Each of these rocks is what fraction of a penny, right? Like if we ground up all these rocks and got all the copper, we wouldn't even have a penny.
I mean, you just have to coat them.
What's that? Go ahead, what?
But you just have to coat them.
Yeah, that's right. I'm not even sure we have enough here to coat one penny, though. Yeah, a penny today is less than 5% copper, I think. But my point is, these rocks don't have a lot. It's not worth a penny of work to get this copper out. So you're looking at what's called low-grade ore. Not economically viable to extract the target substance. Low-grade ore. Not economically viable. If it had more copper, then it might be worth it. If you had $1 of copper in every rock and it only cost 50 cents to get it out, that would be pretty high-grade ore. That would be economically viable. This is not. When you talk environmental science and you talk extraction, one of the things that I'm always reminded of is how difficult it is to actually get the stuff we want out of our planet. Like if you want to be a hunter, it's pretty tough to get a shot at a deer. And if you want to be a commercial fisherman, it's pretty tough to find the right fish. And if you want to be a miner, it's pretty tough to get the metal out of the rocks. We should get our words right. The blue stuff is the target material. That's the resource. That's the copper in this case. Resource or target material. And the rock which has the target material, that's called ore. O-R-E, ore. There are three main ways to get the metal out of the rocks, and I got to teach you those because that's the end of number 16. If you want to pass up those rocks, I'll need them later for a demo. One way that I could get the copper out of these rocks is reversing the way that the copper got into the rocks. Please look up. Option number 1 is called smelting. You just cook the rocks. You melt the metal out of the rock. Smelting is just melting. That's option numero uno. And it's a pretty simple process, actually. If you want to do it cleanly, it gets difficult. But the basic idea of smelting is that the metal will turn liquid before the rocks turn to lava. So you just light it on fire until it gets runny, and then you catch all the melted copper, and that's the end of smelting. Smelters are huge furnaces where you burn usually coal, generate tremendously high temperatures, and turn the target metal into liquid so that it'll pour out of the rocks, and then you capture that liquid and you mold it, and now you can take it to the bank and sell it. Some of you understand that different metals have a different melting point. So if you have a whole bunch of mixed metals, you can adjust the temperature, and that's a way to distill or separate your metals. So you can do fractional smelting, where first you get the lead, and then you get the gold, and then you get the copper, and last you get the iron. Because they have different melting points. And this process, please look up, is the main source of historic acid rain from all that coal. And, you know, when you heat up those rocks, a lot of them have other ingredients in them. So there's a lot of miscellaneous toxins that go into the air. You know, because of the energy use, which is usually coal, you get the SOx and other miscellaneous toxins from whatever was in the rock. Yeah?
Sorry, you said that was acid rain?
Yeah, I remember that SOx are the most dangerous type of oxides in the air because they produce the strongest acid rain. Claire, last week you recorded, not streamed.
I did?
Yes.
Oh,
It's fine. I was able to record in periods 4 and 5.
sorry about that.
It's fine. But this one may not be contiguous, so you gotta leave it set up so that I can record in 4 and 5 later today as well. And just watch for that.
Yeah, my bad.
Okay. Okay. So smelting is just to melt out the metal. You use coal for that. Tremendous energy usage, a lot of SOx in the air, and a lot of other toxins when you heat up rocks that much. Anybody want to talk more about that one? Next, please look up. I bought a set to show you this. Then I realized I gotta buy a new set every year, and I get hazardous material to dispose of. So I stopped doing the lab. Now we can just pretend the lab. If I wasn't such a cheapskate and a lazy old man, I would take, please look up, 2 coffee filters. Put all that ore on top. And I would pour pretty high strength sulfuric acid onto those rocks. That sulfuric acid would pour over the rocks, separate the copper from the rock. It would also separate most of my flesh from the skeleton, and it would splash on the ground. Got it? I could probably use a different tool and recapture that sulfuric acid. If you wanted to go to Miss Solanke and Miss Rivera's chemistry lab, you could do heap leach extraction with really good cleanliness. You would end up with clean quartz that would need to be rinsed off and could go back into the ground. And then you would end up with a coffee filter with a little sprinkling of brand new shiny copper. It would look all pretty and that coppery shiny color like a brand new penny. But please look up. The problem is that in an industrial scale, it's tough to contain that much acid. You get some stuff left on the rocks, you get some spillage, you get some splatter, you get some acids that evaporate, or crystals that fly away and mix with water someplace else. So it's really easy to do that in a chemistry lab, and it's really tough to do that in industrial volumes. That stuff is called heap leach extraction. It's done for all sorts of metals. You make a heap of the ground up rocks, and then you leach the metal out of the rocks with some sort of strong acid. I believe it's usually sulfuric acid. I think you can use others. I don't know for sure. Probably better not be on your cell phone, because it looks like it. Next. Does anybody know the answer to the warm-up? What happens if you eat pure 100% elemental mercury?
Doesn't it kill you?
Nope.
Nope.
Anybody else? Yeah.
Right through you.
It goes right through you. And then you go to poop and it goes clink in the toilet. How many of you were surprised by that answer? There's a detail that we have to clarify. And just so you know, I'm intentionally oversimplifying something which would probably kill you. So don't eat mercury. But I should explain this a little bit further. Your cells don't really have a lot of toxin prevention filters. Your cells are not very smart about keeping stuff out. Your cells are just swimming in all the juice that makes you you. And they don't have to be that picky about what they keep out, because they're really choosy about what a cell brings in. Each different cell type in all your different organs has a different set of bouncers or gatekeepers that are picky. They say, oh yes, this material can come in, everything else you're just staying out. You understand what I mean by that? Your cells don't keep stuff out very well, they're just selective about what they let in. One thing that's funny, your cells evolved in a really simplistic time. Your cells, almost all of them, love carbon. Because in nature, carbon is only found in a few really good things. Metabolically, for your body, if it has carbon and you're in the wild, the environment where you evolved, if it has carbon, that's good for you. What compounds would have carbon in the wild? Sugars, lipids like fat and starch and stuff, like you need all that. That's why our flavors are selectively choosing those, because those are rare in the evolutionary landscape. Your cells are not choosy. They're like, oh my god, carbon, just get in here. We need carbon for metabolic process. You understand that? Here's the problem. Your cells do not absorb mercury. Your cells do not have any particular interest in mercury. Remember what I said, they're not picky about what they keep out, they're just picky about what they absorb. There's no part of your cell that grabs mercury. Like pouring marbles over your head, they just tumble through. There's nothing to grab those and bring them in. But watch this. If that is methyl mercury, now, you all see that? That carbon atom? Your cells will grab that. This is part of the lost lectures of December. I'm sorry that I didn't make this a bigger point so far. I am planning to give you this lecture later. But most years, when I get to Unit 9 and I say methyl mercury, the students have had a couple of other lectures and they're like, oh, that's the dangerous stuff. Since you didn't get that, I have to clarify. That mercury in and of itself is not dangerous to you because your body doesn't really absorb it. You got to do some really wacky stuff to get straight elemental mercury into your cells. But if it is attached to carbon, then you're screwed. Can I give you that last caveat about eating mercury? First of all, you'll probably never be able to find pure elemental 100% mercury, so you should never eat it. And second of all, mercury is methylated by microbes, and you have microbes in you. So even if you did eat elemental mercury, it might become methylated, and then your body would absorb it, so you shouldn't. But there's the distinction. Elemental your cells don't use, methylated your cells think is useful because of the carbon. Now, the third way that you should know how to separate target material from ore, please look up, is called mercury amalgamation. Reminder from Friday, rainforest has a lot of rain, so rainforest has a lot of water, so there's a lot of rivers, so there's a lot of placer deposits. And so, please look up. One of the world's leading suppliers of gold is illegal mining in the tropics, where there's all those deposits and all those rivers. And I told you already that this is the gateway for tropical deforestation, the one activity that's profitable enough to drive people into the really dangerous, sketchy, truly virgin rainforest. The gateway activity. I told you already that this is one of the biggest impacts on tropical rainforest, and it's associated with all sorts of horrific evils, like people eating rare wildlife, like the human slave trade. And now comes the bonus. Mercury amalgamation is basically illegal everywhere. I don't think that you're allowed to do this in almost any part of the world. But since you're already breaking 7 or 8 laws, why not break one more? Mercury amalgamation is a really, really cheap, simple, low-tech way to refine gold. And you have to know that. Mercury amalgamation is like the pirates' gold refinery. It's super low tech. 2 barrels and some fire. You take a whole bunch of gold ore. Watch this. You pour in mercury, heat that up, and mix it. The mercury amalgamates the gold, which for many of you is a vocab term. Amalgamation is a mechanical bond between metals, not a chemical bond. It's like mixing Play-Doh. They just kind of blend together. Now that the mercury and the gold are amalgamated, that they're blended together, things get really, really gross. You separate out all the rocks because mercury's heavy, it sinks. So when you're stirring it all, you'll get a layer of rock on top of a layer of mercury gold amalgam. Then you take the mercury gold amalgam. Sorry that you have to know this one detail. You add nitric acid, H2NO3, nitric acid. And in that acid, those 2 metals separate. The mercury and the gold will separate. So you pour the nitric acid and the mercury into the river, and you're left with a whole bunch of gold. This is totally horrific, totally illegal. It was done all over the United States back in the day. That's why you're not supposed to eat rainbow trout in the rivers where people used to mine for gold. How many of you have been to, did we ever talk about Red Rock? Do you all know where Red Rocks is? Like on Paradise Road? How many of you know what I'm talking about, Red Rocks? Just checking. So when you go to Red Rocks, parking lot, walk up the water, there's the big tall jumping rock that's super sketchy where I saw some guy jump and hit a rock. You walk like 45 minutes or an hour upriver, and you get to this one big sign on a post that says, "Do not fish, illegal to eat, trout, mercury poisoning danger, do not consume fish, wildlife from this river." That's because higher up on that river, they used to mine for gold, and they would amalgamate it with mercury, and they would pour that mercury into the river, and once that mercury is in, microbes stick on a carbon, and that mercury builds up in wildlife. The wildlife all think it's useful because it has carbon, so they store it in their cells. Please look up. You have to know that mercury amalgamation is mostly illegal. It's associated with those remote illegal gold mines. And it is one of the world's leading sources of methyl mercury. The mercury in seafood. Wacky thing about this is that that's mercury in freshwater fish. So when I went to Manaus, which is kind of like the epicenter of Brazil's Amazon rainforest, I got to eat a couple of big predatory fish. And I was talking to the chef who, you know, like knows the guy that catches the fish. And I was like, wow, man, do you love this fish? And he's like, well, around here we don't eat it too much because it has really elevated mercury levels. So if you just eat it once or twice, it's not a big deal. But if you were to eat it often, you know, it could be bad for you. The highest levels of mercury ever found in fish are not tuna and sharks in the ocean. They're freshwater predatory fish in Brazil. I believe the largest levels of mercury ever found in a fish were in arapaima or in tiger shark, or red-tailed catfish. Big predators of the Amazon. And we're done with number 16. And this is where I've stopped all my other classes because they can barely get to this point by the end of the day. Derek, would you please turn off the stream?